Hello everyone, my name is Kabir Tomar and I'm here to present on commitments from Quantum One Wayness, which is joint work with Dakshita Khurana from UIUC. Modern cryptography began with breakthrough schemes for public key encryption such as RSA and Diffie-Hellman, which are also the first schemes that were proven secure. And proven secure means that their security was based on assuming that certain number theoretic problems were hard. And the downside of building schemes based on the hardness of specific algebraic problems is what if one or more of these hardness assumptions turns out to be false? Well, then our scheme is no longer secure. So this insecurity naturally leads to the following goal, which is the holy grail of theoretical cryptography, which is we want to base our primitives on the weakest possible complexity assumption in order to hedge our bets against our assumptions turning out to be false. And we want it to be a complexity assumption because these generic assumptions can be instantiated from a variety of concrete problems and they tend to be weaker than specific assumptions. In the classical setting, it is known that a simple complexity assumption, known as a one-way function, is necessary for all classical cryptography, which is to say that the existence of any classical cryptography will imply the existence of one-way functions. And what is a one-way function? It is a function such that f of x can be efficiently computed for all inputs x, but finding the inverse f inverse of y is not efficient for some random y. Now things are a bit different once we add quantum computing to the mix, and the reason for this is that we can relax or even remove some assumptions by using quantum resources instead. For example, quantum key distribution is possible without making any computational assumptions. Now, a lot of useful and central cryptography, such as bit commitments and multi-party computation, do require computational hardness assumptions. However, some recent work has shown that these primitives can be based on assumptions that are potentially weaker than one-way functions. To put it in other terms, one-way functions are equivalent to a lot of useful cryptography like commitments, digital signatures, pseudo-random generators, secret key encryption, and one-way functions are also implied by all known classical cryptography. However, there exist some quantum cryptographic primitives which are known to be implied by one-way functions. However, one-way functions don't seem to be necessary for their existence. And we can say something stronger here, which is that there exists an oracle relative to which p is equal to np, which means that no classical cryptography exists, no one-way functions. Yet these quantum cryptographic primitives can still exist. So there is potential for cryptography even if p equals np, which is to say cryptography without one-way functions. And in this sub one-way function domain, the major open problem has been what are now the assumptions that are minimally necessary for cryptography. And there have been two major candidate minimal assumptions, which are called one-way states and EFI pairs. And one-way states, in some sense, capture the hardness of quantum search problems, and EFI pairs capture the hardness of quantum decision problems. And what do I mean by that? First, let me define these two objects, and we'll start with one-way state generators, which can be thought of as a quantum analog of a one-way function. So they consist of two efficient algorithms. One is the keygen algorithm, which takes in the security parameter and samples a random classical key k. And then there is the state gen algorithm, which takes this classical key k and maps it to a quantum state phi k. And the security property we want from this object is it should be computationally infeasible to invert, which is to say, given some polynomial number of copies of phi k, it should be computationally hard to find k prime such that phi k and phi k prime have some noticeable overlap. For any k prime that an efficient algorithm finds, phi k and phi k prime should be nearly orthogonal. More formally, for all efficient algorithms A that take as input polynomial many copies of phi k and output k prime, the expected overlap will be less than equal to negligible in the length of k. Now, if one-way state generators are the quantum analog of one-way functions, then EFI pairs are the quantum analogs of commitments, stripped to just their bare essentials. And what that means is an EFI pair is a pair of efficiently sampleable mixed states, rho 0 and rho 1. And a mixed state is nothing but a distribution over quantum states. So two efficiently sampleable distributions that are statistically far, which is that an unbounded time distinguisher can distinguish these two distributions. However, they are computationally indistinguishable. No efficient algorithm, given a sample from one of these two distributions, can tell which distribution it came from. I will situate these primitives in their context by showing their relationship to the broader landscape of quantum cryptography. And which is to say, most quantum crypto primitives end up implying one or the other of these two objects. So digital signatures, pseudo-random state generators, variants of quantum money, and one-way functions all imply one-way state generators. And EFI pairs are also implied by pseudo-random state generators, one-way functions, and are in turn equivalent to quantum commitments, computational zero knowledge for NP or QMA, and secure multi-party computation. The relationship between these two objects, however, was, before our current work, unknown. And this is surprising because their equivalents in the quantum setting, which is to say one-way functions and classical commitments, are known to be equivalent. But in the quantum setting, there are many barriers to proving any such equivalence. And in our work, we overcome some of those barriers to show that one-way state generators with pure state outputs imply EFI pairs. And as a consequence of this, pretty much everything in quantum cryptography ends up implying EFI pairs, which is good evidence that EFI pairs are a good minimal assumption for quantum cryptography. Now, our results can be separated broadly into two theorems. First, we show that pure one-way state generators imply some simple objects with classical outputs, which are referred to in the literature as one-way puzzles. And we believe that these one-way puzzles are interesting in their own right. Next, we show how to use a mixture of classical and quantum techniques to build EFI pairs from one-way puzzles. But first, let us warm up a bit by looking at how EFI can be built from classical one-way functions so that we can better understand what the difficulties are in the quantum setting. And here we are going to show how EFI can be built from injective one-way functions. And recall that a one-way function is a function that is efficient to compute and difficult to invert. And the goal when we are building EFI is that we want to have two distributions that are efficient to sample from, statistically far, and computationally indistinguishable. Now, the Goldreich-Levin theorem gives a simple hash function such that for a one-way function f and for a randomly sampled x, f of x appended with the Goldreich-Levin hash of x is computationally indistinguishable from f of x appended with a random string. And this symbol, the squiggly lines with the C, this means computational indistinguishability, which means that no efficient algorithm can tell the difference between these two distributions. And now we have these two distributions, f of x with the Goldreich-Levin hash of x and f of x with a random string, that are computationally indistinguishable. They're both efficient to sample from, and they are statistically far because f of x, f being an injective function, determines x, which in turn determines the Goldreich-Levin hash of x. So in the first distribution, the Goldreich-Levin hash is determined, while in the second distribution, it is simply a random string. So these two distributions are statistically far, giving us EFI. But what happens if f is not injective? Then f of x does not fix a single x. There could be many preimages of f of x. And therefore f of x does not determine the Goldreich-Levin hash of x. What this means is that these two distributions are not necessarily statistically far, and in fact, they may be identical. And this brings us to the core idea from the seminal paper that shows this construction, which is, can we construct an injective one-way function using any arbitrary one-way function? And the answer here is no. But we can construct a one-way function that is injective most of the time. And what we want to do to achieve this step is we want to reduce the number of preimages so that most of the time f of x just has a single preimage. The tool we will use to do this is something called a pairwise independent hash, which is a hash function, a statistical hash function with the following property, that for any x1 and x2, the probability for over the randomness of the hash seed, that hash of x1 and hash of x2 are the same, is 1 by the size of the output space. So it is the same probability as though both of the hash outputs were chosen uniformly at random. And as a standard, we will abuse notation slightly and use small h to refer to both the key and the function corresponding to the key. So the goal of using this hash function is we want to eliminate the ambiguity in preimage given f of x, because given f of x, we don't know what the preimage was. It could be x, it could be x1 prime, x2 prime, x3 prime, all different values that collide on f of x. So by giving out more information about the preimage, we want to eliminate this ambiguity and therefore fix a single preimage. And we do this by appending the hash of x to the function output. And if we choose the length of our hash correctly, it is unlikely that any other preimages of x will collide with x under the chosen hash function, which means that the overall function will be injective with high enough probability. Now it is crucial that we choose the length of this hash output correctly, because if the hash output is too short, say a single bit, then this single bit is not going to help us very much in disambiguating between all the possible preimages of f of x. But if the hash output is way too long, then we may end up leaking too much information about x, and then f of x will no longer be one way. So the value we need to hash to is approximately the log of the number of preimages of f of x. Now if we replace f of x with our almost injective one-way function, which is f of x concatenated with the pairwise independent hash of x, we can see that f of x along with the pairwise independent hash of x determines x with sufficient probability. And therefore, these two distributions are computationally indistinguishable, and now they are statistically far as well. However, in general, the number of preimages of f of x is not efficiently computable. So we don't know how to correctly find the length of this hash, and the construction is not yet efficient. We will return to the efficiency issue, but the crucial thing to remember right now is that the length of this hash depends on the number of preimages of f of x. Now, suppose we want to build EFI from one-way state generators. Well, if one-way state generators are the analog of one-way functions, what happens if we simply replace the one-way function with the one-way state generator output? And if we do that and we use the Goldreich-Levin hash of x, we do in fact get two distributions that are efficient to sample and computationally indistinguishable. However, if our one-way state generator is not injective, we will still need to append the pairwise independent hash of x. And again, the length of this hash of x will depend on the number of preimages of phi of x. And this is where we run into our first barrier, which is it is unclear in the quantum setting what a preimage even is. And the reason for this is a primary difference between classical and quantum information is that quantum states can have overlaps. So a single qubit can be in the 0 state, it can be in the 1 state, but it can also be in a state that is a linear combination of 0 and 1, which, for example, it could be in an equal combination of 0 and 1, which is referred to as a plus state. And this plus state, in general, cannot be perfectly distinguished from the 0 state. For any statistical tests that you apply that the 0 test passes, the plus state will also pass this test with some good probability. And what this means is that the plus state fundamentally has some of the same properties that the 0 state has. So a consequence of this is that the notion of a preimage for this quantum state is not well defined. Consider, for example, two quantum states, phi x1 and phi x2, which are respectively the outputs of our state generator on input x1 and x2, where x1 and x2 are two classical keys. And also suppose that these two states have some noticeable overlap. The question I will ask is string x1 a valid preimage of state phi x2? Now, any adversary that on input phi of x2 manages to find and output the value x1 would be breaking the security of our one-way state generator, because it is outputting a key that maps to a state which has high overlap with its input state. So we cannot simply say that x1 is not a preimage. However, we cannot claim that it is a valid preimage either, because it does map to a detectably different quantum state. So the notion of a preimage starts to break down. Now this problem only arises because of these partially overlapping states that are close to each other but not exactly same. And a natural approach to try to get rid of this problem is therefore try to eliminate all such pairs of states. And one way to do that is to repeat in parallel. Parallel repetition has the effect of taking states that were somewhat overlapping and making them almost orthogonal. However, this approach fails in our case because even though it takes these partially overlapping states and makes them nearly orthogonal, the same process would also take states that are actually really close enough to be treated as the same state, and then map them to states that have some partial overlap. So it eliminates some partial overlaps but ends up creating even more. So we need to employ a different tactic here. And note that this problem does not arise when our outputs are classical strings. Two classical strings are either identical or orthogonal. There are no partial overlaps. So, as a strategy, we can try to obtain some one-way object which has classical outputs instead of these quantum outputs. And the natural approach here is we can try to obtain a classical description of our state phi k. And the process that performs this is something known as quantum tomography, which takes in a number of copies of some quantum state, applies this tomography process, and ends up with this classical description of the state. The problem with this is, in general, the size of this description is exponential because general n-qubit states do not have polynomial size classical description. So any classical encoding that we do generate it cannot be exponentially sized, it will have to be polynomially sized. So it will have to discard a lot of information. And that can be quite bad for us because what if the computational hardness is all encoded in this information that we are going to have to throw away? Well, in this work, we show that there is a way to compute efficient classical descriptions of quantum states that do throw away a lot of information about the state, but still preserve the computational one-wayness. And the tool we will use for this is a recent tool known as efficient shadow tomography. And what efficient shadow tomography does is it takes a polynomial number of copies of a quantum state psi and computes this classical string known as a shadow for this quantum state. And this shadow cannot be used to recover psi, but it can be used to estimate a limited set of properties of psi. More formally, there exists an inefficient estimation procedure that takes as input the shadow and a key k. And what this estimation procedure does is it computes a very close estimate for the overlap between phi k and psi. So there is an inefficient algorithm that nonetheless allows us to compute overlaps with any phi k for our given psi. And the fact that this shadow procedure preserves overlaps allows us to replace phi of x with the shadow of phi of x in our previous constructions, which means that the output now becomes classical. However, with some work, we can show that inversion will still remain computationally infeasible. So we have this classical output, classical input object, which is nevertheless computationally difficult to invert, and we define one-way puzzles to formalize the properties of this object. And what is a one-way puzzle? It can be thought of as a sampler for hard problems along with their solutions, where solutions do not need to be efficiently verifiable. Namely, there is this generation algorithm which randomly samples a puzzle P and a key K, which can be thought of as a problem and a solution. And the security property is that it is hard to find a valid key for a randomly sampled puzzle. And we may think of the key being valid if it passes some potentially inefficient verification process for the puzzle. Now, the fact that solutions do not have to be efficiently verifiable is very unusual for a cryptographic primitive, and we find it somewhat surprising that we can build useful objects from this kind of unverifiable hardness. However, we do think that one-way puzzles are interesting in their own right, and this is because on one hand, they model this quantum process that samples hard problems with solutions and can be thought of as a randomized variant of one-way functions. And we can also show that one-way puzzles are, in themselves, a necessary object for the existence of hybrid cryptography. And hybrid cryptography is cryptography where locally parties are allowed to do quantum computations. However, all communication must be classical. Additionally, because one-way puzzles are this classical output, classical input object that can be used to simplify several separation results and hopefully help prove even newer ones. And next up, we will show that this one-way puzzle object implies the existence of EFI pairs. So now we have this classical output object which solves our overlap problems. So we can try to apply the previous ideas from Hill to one-way puzzles. And recall that our goal is to end up with two distributions that are efficient, statistically far, and computationally indistinguishable. Naively trying to apply ideas from Hill here, however, encounters a second barrier. Consider some keys x1, x2, x3 that all map to the same value y under this one-way function. Now, when the key is chosen uniformly at random, as it is in our candidate distributions, given that the output is y, each of these keys has an equal probability of being sampled. And the way I put it is, given that the output is y, the pre-image distribution is flat. There are some points which have the same probability of being sampled, and all other points have probability 0 of being sampled. And it turns out, for the ideas from Hill to work, for us to find that exact right hash length, this distribution needs to be flat. In the quantum case, however, because these keys are being generated by a quantum sampler and not being chosen uniformly at random, this distribution on pre-images can be arbitrary. It can be spiky in some places, low in some places, and is not required to be flat. Now, the techniques of Hill crucially rely on this flatness, so we need to find some way to maybe convert this to a flat distribution. And the core idea here is we notice that for any distribution, there is always some subset of pre-images, which we call a slice, that both occurs with noticeable probability, and while it is not exactly flat, all the probabilities in this slice are very close to each other. Close enough that the Hill techniques can be applied if we are restricted to just this slice. So, more precisely, we make the following modifications to our construction. The first change is, since we don't know what the length of the hash is, we will sample randomly and hope to get it right. This is just a standard trick in the classical setting as well. And the more interesting change is, in the second distribution, we change the final bit b. Instead of always sampling it uniformly at random, we set it to be identical to the first distribution unless some specific good event occurs. And this good event is defined as the sampled x belongs to the good slice and we guessed our hash length correctly. Now, unless this event occurs, both these distributions are identical, and condition on this event occurring, our x will be in our good slice, so we can apply our Hill techniques, and the hash length will be correct. So these two distributions will, conditioned on the good event, be computationally indistinguishable. Now, with a good deal of work, we can show that these two are statistically far as well. And in fact, we can show that the second distribution has more entropy than the first distribution. However, because it is not efficient to tell when x is in the slice or if we have guessed the right hash amount, the second distribution is still inefficient. But using entropy extraction techniques, we are able to convert these two distributions into two efficient, statistically far, and computationally indistinguishable distributions. And I will not be covering those techniques here. For a better overview, I recommend you take a look at our paper. I will add one final point. In the classical construction, at some point, a non-uniform construction is converted to a uniform construction using an object known as a combiner, which takes in several candidate constructions and outputs a single object with some security property. And in the quantum setting, the classical combiner does not work, and so we came up with a novel combiner for commitments to get rid of the non-uniformity. To conclude, we show that one-way state generators imply a classical input, classical output object known as one-way puzzles, which are in turn implied by hybrid cryptography, and finally one-way puzzles imply EFI pairs. And I'll quickly touch on some open problems. One is whether one-way state generators can be built using EFI pairs. The other is whether hybrid cryptography can be built using one-way puzzles, whether one-way state generators can be used to construct the quantum analog of pseudo-randomness, and finally whether this restriction on pure state outputs can be removed. And there has been recent exciting work on this last problem. That'll be all from me. Thank you very much for listening.